Hey everyone, welcome back. In this video, we'll be solving Churchill. So before we start the video, don't forget to follow me on Twitter and don't forget to hit the sub button. And if you have any questions, either on this video or the other videos, don't forget to put a comment too. I will be glad to just answer your question. Yes. So let's not waste too much time and see what we have. So overview. So this log ID is enter new management. All the vulnerabilities in our old logs are now resolved. So this is just some details, and we have so this log accepts a program from the old password input prompt. Only programs signed by us are allowed, and this is the program. Well, this challenge looks like the same as Cold Lake, and Halifax, but I don't know yet, but this format we have seen this format before. So okay, so let's try to run the card and see what we have. So enter a payload. So let's say I'm going to be, for example, saying that I will be sending this program since we will be using this one. So if we run the card, what we have. So if you continue, we see that this program is just the same thing. So it is basically a loop, an infinite loop, I think, or something, where each time, if we don't, if we don't give, for example, the right payload, it won't be executing. And I don't know exactly if this payload is executing or not. So that's why we have to reverse engineer back the code to just understand what this code is doing exactly. So yes, so if we search for the main, so this is the main. So he is adding, so basically he is adding this negative value to the stack pointer, which means that he is basically allocating space on the stack. So what else? We have welcome to the secure program loader. So this is a message. This is another message. We don't have to care pretty much about what is happening about the messages. So we have memory set. So he's going to be setting. So this is the size of this space. So this is the source, which is going to be 0x0s, and this is going to be the destination, which is 0x2420 as the address. And he will be setting the space starting from 0x2420 to zeros, basically. Yeah. So once we have finished that, what we have? So we will be reading the input, which is the payload to be debugging, so that it will be debug. So this is the size of the payload. So this is the address. So this is the destination address. This is reading the payload. So we will be reading the payload into this address that we have already set to 0. So this was just initializing the space with zeros. Well, what do we have next? So we will be moving. We have seen this pattern in the Cold Lake and Halifax challenges. So this is basically just retrieving the first 2 bytes from the payload. So that means, for example, when we say that, let's say, if we refresh again a little, so I'm going to be copying this payload. So for example, if we have this payload, which is this one, um, so let's say for example we wanna see what this payload is doing. So let's try to. So basically, he is dissecting, or he is just parsing this payload. So let's see what's going to be happening exactly. So we will be moving into a register 11. Um, the first byte that is located in the payload. So that means that we will be going on 2420 is going to be this one. So this is 2420, this is 21, this is 22, this is 23, this is 24, and so on. So this is basically the character that is pointed to by 2420. So this is will be basically 2420, which will be equal to 80. Then we swap with the bytes and the register 11. So since register 11 is a 2 byte size, so it will be having something like this. So this is what the register 11 will be having exactly. So if we swap the bytes, so register 11 will be 80, so it will be 0x 80 and 00. We have basically just swapped the bytes. And then we will be moving the byte that is located in the address 2421 into register 15. So we have register 15 equals to um, just the 0x00, and we have another 00. So we can just separate the two bytes so that it can understand exactly what is happening. And then we do an OR with the resistor 15. So resistor 15 equals to resistor 15 or the resistor 15, which will be equal to obviously 0x 18 0 0. Since we will be ORing these two values together, these two values together, we will be getting the address. Um, we will be getting this address, which is 1800. Yes. Now, what we have next? So we will be moving the byte that is in here into the register 9. So register 9 is going to be 0x0000, and the register 10 will be having the value 0, will be having the value 6 as a value, and the register 10, since the address 2423 is pointing to this value, which is this one. Now we will be testing, so if the if resistor 11 is, so we'll be testing if it is equal to 0. So if it is greater or equal to 0, then, well, basically, if it is greater or equal to 0, then we'll be jumping to this address. Otherwise, we will be comparing that value at the we'll be comparing that value. Yes, we'll be comparing that value at the register 11, which is the address that we have just generated, which is this one, with the 0xFF with F001. So basically, this is just a simple check that we have just so in the challenges of Gold Lake and Halifax, where he wants exactly the loading address to be in this range, which is from 8,000 to F1000, etc. So we can just skip all of that and go just directly to the next branch. So he will be moving now register 15 equals to register 10. And then he will be adding 0xFFA inside of, so this is a negative value. So register 15 equal to register 15 minus this value. If we go and check this value, so 0xFFA, so this is minus 6, which is 0xFF, so it's just a minus 6. And then he will be comparing that value with the 3BB, with 0x3BB. So basically this is just trying to check the size of the payload, I think. So yeah, so we are basically checking the length of the payload. So if it is invalid, then we are in the exit branch, I suppose. So he'll be just calling that and jumping exactly to, he will be jumping back to the beginning of the code and reading another payload. Yeah, so this is just a branch check the size of the, or let's say the length of the payload. Yes. What else do we have? So after checking the range of the address and after checking the payload length, we came into another branch, which is now, we don't know yet what this branch is going to be doing, but let's try to reverse engineer it also. So register 8 is going to be having register 11 or register 10, I'm sorry. So register 8 then will be equal to register 8 plus 0x2420. So that means Since the register 10, as we have seen, is going to be this one, so he will be basically jumping, um, he will be basically jumping all those, since this is the address of the 2420 plus 6, we will be landing on this place exactly. So this is just actually trying to do, so we can just say, but for example, like, um, we can say just one thing, one interesting thing, guys, is that the payload lands. Why did we subtracted 6 from it? This is a question that is a really interesting. So basically, if we try to see this, so we have, for example, in this case, we have, for example, 1 byte, 2 bytes, 3 bytes, 4 bytes, and etc. And then we have something, and as you, if you remember the challenge of the Cold Lake and the Halifax, we basically, this is the address where we will be loading, the payload, and this is right now something that we didn't see before, and this is basically the size of the payload, and this is supposed to be the payload. Well, this is supposed to be the payload or the code that we will be executing, plus the digital signature that we will be using in order to execute the code that we will be loading. Yes. So this 6 is basically getting exactly the size of the payload. Yes. So this is just getting the size, exactly the size of the payload. So for example, in this case, we have to exactly know the size of the payload. So register 10 will be basically just having register 10 will be having exactly the size of the payload, and yes, and this is the code that we will be executing. So if we try now to see exactly how, if we want to go exactly to the if we want to exactly go to the code in the payload, so we just have to jump with the size of the payload that we will be executing. So the conclusion is that this is the size of the payload, or let's just say the size of the payload. Yes, this is for now unknown. We don't know exactly what what this value means exactly. And register 10 is loading address, where we will be loading the payload. Yes, so register 8 now will be pointing to the payload. Yes, so now register 13. So we have a call to the memory copy, so it's supposed to be the size. So we will be copying the payload to the stack pointer. Okay. So we have just to wait a second. So we'll be jumping 6 bytes. So 1, 2, 3, 4, 5, 6. So I think this is not the size. So we are basically jumping with the size of the payload, but at the same time, I think this is the digital signature. So register 8 will be just holding the offset of the digital signature. So this is just the offset of the digital signature. So we'll be passing down the offset of the digital signature, and we'll be passing also um, the destination address. So this is the destination address, which is going to be the top of the stack. And don't worry, guys, after just doing all this static analysis, I will be trying to decompile the code with you, just to try to write something and see that is comprehensive, much more better than this one. Yeah, so then we copy the signature to the top of the stack. Yes, after doing that, so we go and we came back to check if the register 9 is equal to 1. If we go back, register 9 is containing a value that we don't know. We can just call it flag, for example. Or we can call it, I don't know, a hole or whatever. Let's just call it flag. So if the flag is equal to 1, then, well, we jump if it is different to, if it is not equal to 0 to this address, which is plus x1c. But if it is different to 1, let's say it is different to 1. So if it is different to 1, then we will be passing down register 13 equals to the stack pointer, which is basically the digital signature, and register 14 will be equal to the size, and we will be passing also 0x20. Yes, we will be passing down 0x20. So register 15 will be equal to the address 2420, which is the beginning of the payload. And then we will be hashing basically what is going to be. So this is basically is supposed to be the destination, I think. Yes, this is the destination, and this is the source, and this is the size. So we will be basically, so this is the destination, this is the size of the input, which is equal to the size of the payload, I think. What else? So, and this is basically the source, I think. The source that we'll be hashing. So basically we'll be hashing, in our case, for example, in here, since we have gave it 6, so we will be hashing basically this part, because this is a 6 byte size. So yes, we will be hashing that one. So after hashing that one, we have register 13 equals to 0x40, which is, if we go and check just a little thing, just one more thing to check, what is the size of this thing? What is the size of this thing? So if we go back a little, starting from C226, which is this one. Let me just go and check the length of this one, because it is something that is repeated. Okay, just a second. Yeah. Yes, so what is the length of this one? So it is 128. If we divide it by 2, uh, if we divide it by 2, we get 64. And 64 in hexadecimal is 0x40, yes. So yeah, so I guess, or I think this is the size of the digital signature. So this is the size of the digital signature. And then what we are going to be calling is memory copy. Okay. So register 8, register 14. So register 8 is the 24 20 plus the 0x6, which is this one, I suppose. Yes, so it is the offset of the digital signature. So this is um, this is the offset of the original one, that the original digital signature that we have passed down. So offset of the original digital signature. And by the way, the SHA-512 is going to be returning the result of the stack. So the destination is going to be in the stack, basically. Yes, so then he will be passing that hash. So the hash of the payload. So of the payload. So it's going to be the hash of the first 6 bytes. Well, in our case, it's going to be the 6 bytes, but at the same time, it is going to be the hash of the 6 bytes of the payload. And then we will be memory comparing them. So we will be comparing the hash of the first 6 bytes of the payload with exactly the original digital signature. So by looking at this, so we'll be basically hashing those together, and then we will be comparing the hash of that part exactly with this one. Yes, so this is what is happening, and then we'll be testing if the resistor 9 is if the so and then we'll be jumping basically to this address. So what does this address is going to be doing? Yeah, so this address is basically this one. So and then we'll be jumping to check if the resistor 15, which is the result of the memory copy, is 1. So if the resistor 15 is equal to 1, then we will be just so we jump if it is equal to 0. So that means if the resistor 15 equals to 1 to this signature valid and executing payload. And so we move the resistor 10, which is the size of the payload, to the resistor 13, and then we move 24 to the resistor 14. If you go back, what is 24? So this is 0, 1, 2, 3, and 4. So basically, I think this is the code that we will be executing. If we go back just a little, so we move this to the resistor 14, and then we move the address where we'll be loading. So this is the source address, this is the destination address, and this is um, the size of the payload. And this is copying the payload to the loading address. Okay, and then we will be just calling register 11 with the address, so executing the code. Well, in our case, the code that we will be executing is 1341, which is the same as this one, which means that he will be just executing a return. Okay, so this is just an example, I think. So after doing all of this, we have now the other branch now. If the flag, so you did that if the flag is different to 1. Otherwise, if the flag is equal to 1, he will be passing a signature verification process. So what will be happening is that he will be, so this is the offset to the original digital, to, let's say, to the original signature. This is the size of the payload, or let's say in our case, the size of the payload, and this is the payload itself. And this is 24. No, wait a second, just a second. 2420. Okay, I think this is. If we go back just a little, 24. So 2420 is supposed, I think, to be this signature. So one of them is. Yes, so this is the payload that we will be executing. And there is this interesting thing which is at 2400. Now if we go back just a little and we check that out, we see that if we run this program, there is this these bytes which are, we have basically a 32 bytes of data that are already preloaded in the memory. So in order to verify any kind of signature, we need a public key. So this is basically the public key. So yeah, so this is the public key. And by doing that, we verify the identity of the user who is trying to execute the program. Yes, so if the signature is valid, then we will be executing your code. If the signature is not valid, that means that you were not the one who signed the code, that we won't be executing the code. So, and a valid signature of type or whatever that message was. So yes, I think now since we have understood, or since we have reverse engineered this code, I think it is time to write a version that is in C, so that we can completely understand what is happening, or so that we can after just reverse engineering the code, we can find exactly what are the entry points that we can start from. So if we go just back a little, what do we have? So okay. So I'll be just trying to define some I'll be trying to define some constants that we will be using. So the first constant that we will be using is that we know that where is the get string? So just a second. Let me check something out. If these what is this? So we have this constant which is the memory set that he will be using a lot. Whatever, like we don't have to define that one. Let's just try to define the parts of the payload that we will be using, which are the destination address, in this case this one, and the this one, which is the flag, and the size and the code and all those addresses. So if we define them, so we define and then we can just type def since they are 2 bytes size, we can just set them as short. So 0x24, so 20. This is basically the destination. We can just set that as the destination address, which is at the register 11. What else? So we can also type def d24 as the, well, not the source. It's going to be the flag, since this is the flag. Yes, so this is 20, this is 21. Well, it is 22, not 24. Uh, type def, we can just set another address to be used. For example, 0x24, 23 is going to be the size, I think. Or what else do we have in here? So do we have other constants? Nope, I don't think so. So let's now try to start the main. So the main. I'll be using um I'll be using as a main. So the first thing that we have did is that we have allocated the space. So we have to create a buffer for that one, or we have to create a space for the memory. So stack memory. So it's going to be 0x. Basically, how much is this value? So it is supposed to be um, so it is minus 64, which is 0x14 in 0x40 in hexadecimal, I think. So yeah, so this is 0x40. What else do we have? So next thing after doing that, we'll be just printing some messages. So puts some welcome message, I think. What else do we have? So after doing that, we can just try to we can start, for example, start branching. So after doing that, we have a loop. Since we have a loop, I will be implementing that in the old C in the old C mechanisms. Yeah, so the first thing that we will be doing is we have so we have this message. So just this one. So we have to enter payload message. Yes, so after doing that, so what is the next thing that we have to do is we have this memory set. So we have memory set, um, we have memory set, um, what is exactly the thing that we will be setting? So we will be having this one, so, and we have a 0, and we have we have this address, so we'll be setting basically 0x2420 to the address 0 and with the maximum size of that one. So this is basically what is happening, and next we'll be getting this string at the address 0x24. We'll be basically loading in that address um, with the, well, basically it is 0x300ff, which is 0x300ff. And yes, we get this ring there. So the next thing that we have to check is the address range. So if the um if the now we can just use directly those addresses since we know them. So if the 0x 8000 is bigger than the destination, and or for example the destination is inferior to the other address, which is this one, which is 0xf 0xf000, then put puts exactly invalid address range. Invalid address. Okay. It's invalid address, I think. Yeah. And then we go to begin. We just have to go back to this label that I have set. So otherwise, what else under that? So yes, the payload length. So if the size is inferior to exactly the 6, so he's basically going to be comparing that with a 6. So if it is inferior to 6, then we just print, or we just put invalid payload size or length. And after doing that, so we have to just go to the begin again. If it is invalid, then we go back and we read another payload. Um, Now we came to the part where we have to memory copy that before. So memory copy. So we copy the digital signature to the stack. So we'll be getting the offset of the top of the stack and the offset of the digital signature. So we'll be copying that to the stack memory. So we will be copying that one. So from 0x2420, which is already the destination. So from the destination plus the size, since we will be copying to this address, which is 2420. So after doing that, so we will be copying that address to. So we'll be copying the content from the destination plus size. We can just set it, for example, 0x 2420 directly. So from the beginning of the payload plus the size to the stack memory, we'll be copying 40 characters or 64 characters exactly. So this is basically the offset to the digital signature. So and then we'll be going on and check the flags. So if the flag um, um, if the flag, so basically this is if the flag is equal to 1. Why did I set that different to 1? So yes, it is. So we jump if it is not equal to 0 to that place. So if it is 0, that means that the register 9 is equal to 1. So yeah, so if the flag is equal to 1, then we start. The first thing that we will be doing will be hashing the thing. So we call the SHA-512 to exactly the address 0x2420, and with the size, I think. Yeah, we have the size, and the next thing that we will be, the destination is going to be stack. So stack memory. So we will be hashing what is in the 2420 with a size to the stack memory. So we basically, so the result is going to be is going to be on the top of the stack. Yes. Next, what do we have? So the next thing is going to be comparing. So we will be comparing. So we have a comparison and then we have a jump to this one. So if the comparison, so if the memory copy in this case, if the memory or if the memory compare specifically um, of the address exactly now let's get the addresses. So we have the hash of the first size, and we have the offset to the original digital signature, and we have the size. So we're basically going to be taking um, the stack memory, which will be containing the hash, which will be containing the hash of the first 6 bytes of the payload, with the 0x2420 um, plus the size, I think. Or is it the digital signature? Just let me wait a second. I need to check this out. Yes. So the plus the size is going to be the original, since it's register 8, and register 8 is containing this value, which is 2420 with the size, with the 0x40. So if this is going to be equal to 1, then we just go to we are not going to be going to execute. So let's say I don't know, do I have a code that is, do we have a label that is, I'm gonna be creating a label for the execute. So execute is going to be just calling, execute is just be going to be calling this code, which is the signature valid and all this one. So let's say I'm going to be, I'm going to be calling this one. So executing the code and memory copying everything from these ones, which are the destination address. So I'm going to be getting the destination to the 0x2424 with this size. Yes, 2424 and the size this one. So yes, and after doing that, we can just directly call exactly this one. So I think it is done this way. Yes, we have this one that is, I think this is the way we can we just have one thing, which is this one. Yes, so we basically cast it as a function and we just called it directly. Yes, so the destination is going to be the address where um we will be executing. And then after doing that, we can just go to the begin again. We don't need this return 0 anymore. And yes, I think. So if you go back, so after, if the memory copy of the stack memory with this, if we compare the hash of the first 6 bytes of the payload with the digital signature, and we figure out that it is equal to 1, and then we go to execute. Yes, so yeah, otherwise, so else, if it is not equal to 0, we will be executing this code, which is going to be verifying the signature directly. So the verification is going to be, so we verify ed, yes, so we will be verifying what are the parameters. So we'll be having 2420. Well, before the 2420, we have this one, which is the public key. So 0x2400, and then we will be giving 2420, and then the size of the payload, and then the digital signature in the stack memory. And this should be equal to this should be equal to 1 in order to be open. So if the verification of this one is equal to 1, then you go to execute. Yes. Otherwise, so if that is wrong, so if that is wrong, then we will be executing. Just a second. So this is an else with, so if the flag is a different one, we can just embed another we can just embed another else there. Okay, so we just print, well, it's not invalid flag, it's invalid signature. Yes, I suppose now we have completely reversed the code, if I'm not wrong. We have completely reversed the code. Yeah, so now what is the entry point that we can use in order to solve the challenge? Now we have completely just completed the phase where we reverse engineer, and now it is time to find an exploitation inside of this code. So the exploitation is pretty obvious. Since we don't have a private key, so there is no private key, we cannot sign any code that we want. So, but before signing any kind of code, what is the code that we will be using? So I will be using the code that we have used in Lagos and in Bangalore, which is the same one. We'll be just directly opening up the door without any problem. So we'll be just moving FF0 to the state unit register and then moving it down into the program counter. Just by assembling that, we want just to execute this one. But in order to be executing this code, we have to sign that code, and we don't have a private key since the signing procedure is happens using the private keys. Since we don't have the private key, we have to figure out another way. So the other way is pretty simple. Since there are two conditions, so since if the flag is equal to 1, then we will be going into another logic, which is this one, which will be just comparing if the stack memory, um, comparing what's in the stack memory, which is the hashing. So the hash of the first 6 bytes of the payload with the original digital signature is equal to 1, then we will be executing the payload. So the idea is pretty simple. I'm gonna be crafting this one. So we have the address that I will be loading to is this one, and I will be setting the flag to 1 in order to get into this branch of code, or into this if specifically. And then I will be passing down the code that I will be executing, which is, well, I need to first give the size of the code that I will be executing. So in this case, we want to execute this one. So the size of this code is length of this one, so we divide it by 2, it gives us an 8. So we need to add the other ones, we need to add a 4 to it to get exactly the size. So 8 plus 4 is 12. If we hexify that, then it is pretty obvious that it's going to be C. So the size is going to be the size of that one is going to be 0xc, and then we give the payload. So this is the this is the code that we will be executing. This is the size of the code. Well, this is the size of all this payload. And then we have the flag set to 1, which will be going into this one. And then we will be giving the digital signature of this code that we will be executing. Now the thing is, in order to be able to execute this code, we need to make sure that the memory compare should be returning a 1. And the thing that I know about memory compare, for example, is that memory compare will be returning a 0 if the two values compared are equal, or it will be returning a -1 or a 1 if the string 1 is greater than the string 2, then it is going to be returning a 1, otherwise it's going to be returning a -1. Now the thing is that I don't know exactly if the memory compare that was implemented in this card is the same as the memory compare that was implemented on C. So to go and check that, I had to just go and try to reverse engineer this memory compare to completely understand what is happening. So if we go and check that one, so we see that he is pushing the resistor 11, then testing if the resistor 13 is equal to 0, just in case Just in case you forgot, the register 13 is holding the size of as the size of the two strings that we will be comparing. Register 14 is having the string 1 and the string 2, and register 15 is holding the string 1. And then he will be checking if this size is equal to 0. If it is equal to 0, then obviously we will be exiting the memory compare. Otherwise, we'll be moving the character that is in the register 15 to the register 11, and the character that is located in the register 14 to the register 12. So that means that we are basically just moving the characters that are in the string. So for example, let's suppose I'm going to be comparing this one. So string 1 is having um, hello world, for example. Hello, let's say hello, and string 2 is holding hey. So basically, well, hey with another, the only comparison is that hey low. Yes, so we'll be comparing these two together. So the thing is that we will be moving each time, we will be moving the characters into the register 11 and register 12, and as you can see we are comparing them together. So if they are equal, then we can jump directly to the address plus 0xa, which is this one. So we will be just subtracting -1 from the size and then jumping back. So it's basically a loop. So a simple implementation of a loop. And then otherwise, if they are different, so we will be moving the register 11 to the register 15 and the register 12 into the register 14. And then we will be subtracting them together. And then we will be jumping uh, to the end of the memory compare. So once we have two characters that are different, we are basically going to be returning from the function. So that means that we can simply decompile the memory compare as a function like that. So it's going to be short. It's going to be short. It's going to be returning basically a number. So memory compare. So what do we have? So it's basically going to be taking um, two strings. The first one is going to be an array of characters or a pointer that points to a character. So string 1 and string 2 and short size, and it's not going to be like that exactly, but since we have that one, so while the size is different to 0, what we will be doing is that, so let's suppose I'm going to be creating this to a register. So register 11 is going to be holding a character that is pointing to by the first string, which is basically a pointer to that one, which is the string 1 um, plus, let's say I'm going to be creating also a character. So the thing is that this plus is that means that the register 15 is going to be each time incremented automatically. So, and register 15 is going to be the address is going to be basically directly incremented. So in this case, I'm going to be adding another thing, which is just a simple counter. Just I'm going to be calling I. So it's going to be unsigned, obviously. This is also an unsigned. Yes, so it's going to be equal to 0, so be using this one. So this is the first character, and the second character is going to be this one. So if register 11 is different from register 12, then we will be returning the register 11 minus register 12, which is this one. As you can see, we are subtracting them together. Otherwise, we have also to, just a second, we have also to do size minus minus, which means that we have to decrement the size in order to get out of the loop, and we have to return otherwise e0. So that means that both these strings are equal. So this is exactly how the memory compare is working. So in order to return a 1, so simply we have to figure out first thing the signature of this one, and then figure out another input that when we subtract the digital signature of that input with the original digital signature that we will be generating, then we'll be having a 1, and then which should be equal to 1, and then the conversion should be equal to 1, and the return of the memory copy should be returning a 1, and then the door should be unlocked. So the first thing to do is we have to figure out exactly what is the hash of this thing, since he will be comparing the hash of this input with the original digital signature that we will be given after. So if we go and check this out, let's try, for example, to import hashlib, and the message is going to be hashlib dot sha 512. So m dot update. So I'm gonna be updating this one. So I want to know the hash of this thing, and I want to know what is the hex digest of that one also. So one interesting thing, guys, here is that this this hashing mechanism in the Python is not the same as in the microcorruption. I have tried that several times before solving the challenge, and it did not give the same hash. So the best way to know what is exactly the hash of this thing is to simply just copy it and try to see exactly what is the hash of this thing. So in order to do that, I'm going to be using the challenge itself, and I'm going to be setting a breakpoint after the hashing happens, so that I know exactly what is the hash of that one, so that we can craft something for it. So if we continue, so I'm going to be using now this one. So I'm going to be using this one. Gonna be sending, for example, I don't know, some random signature, for example, AA, BB, CC, or whatever. So we hit the breakpoint, and if we go and check the top of the stack, so this is basically the hash. So it's 0f0 um 72 b4 b7 d3 bf etc. So the hash should be with a size of 128, I suppose, characters, which are 64 basically. It should be 64, which are 64 bytes. So yes, so this is the hash. All that is a hash, so we have to parse that together. So what do we have? She gives us a little. So this is the hash. So this is the hash returned by the function SHA 512. So we can just say that this is the hash of the payload. Okay. Since this is the hash, now we have to give something. So we will be sending the flag 0. We'll be sending the flag 1, obviously. So if we are going to be sending the flag 1, so we will be landing into this branch, or into this logic specifically. So we have to give something um, that is going to be returning in the memory copy a 1. So let's say, for example, I'm going to be sending this one. So for example, if I send a 0, and then I send, for example, an 8, for example, and let's say then I'm going to be sending just, for example, a 1 or whatever, just some random data after that. So this is basically what's going to be happening, that when he will be comparing the characters of the hash of the payload that we have sent, which is this one. For example, he's going to be comparing 0 with a 0, gives you a 0, 9 with an 8, it gives you a 1. And basically he will be returning this one, since he will be returning the register 11 minus the register 12, and then he will be quitting with a 1. And once he returns a 1, we will automatically unlock the door. So it does not matter, we can just simply send a 0 and an 8, and then some random data, for example, zeros or ones or whatever. So we can craft that simply just using, for example, so we'll be sending 0 8 plus for example, some ones multiplied by 120, 26. Yes. So this is the payload that we will be sending as a digital signature with the code. So if we send that, if we use that, basically now we can concatenate everything together. So if we try to send this one, if we reset, the door is unlocked. This is interesting. We basically reverse engineer the code and then we reverse engineer the memory copy to fully understand how to solve this challenge. I hope you learned something. I hope you learned something out of that, I think. Wait a second. We have to solve that on this server too. Yes. Churchill is over, I think. Next one is going to be SD Jones. We're going to be solving this one. And yes, if you learn something, don't forget to share with your friends. If you have any kind of questions, don't forget to put a comment. Or you can just message me on Discord, Twitter, whatever you want. And yes, have a nice day. Bye.